Okay, so hello everyone. Good evening. Am I audible?
Yes, sir.
Okay. So today we'll discuss some basic concepts of mechanical metallurgy and also we'll solve some questions. So first we will discuss elasticity. So my screen is visible, right?
Yes, sir.
Okay. So basically we have three kinds of modulus. One is Young's modulus, so this explains the stiffness of a material. Second is shear modulus. So this is responsible for resistance of sliding past each other. And the third is Burke modulus. So this is resistance to change in pressure. So Young's modulus, as we know, when you draw the stress strain curve, we have the straight portion and then we have a curved line. So the slope of this straight portion, that is our Young's modulus, that is E. Similarly, shear modulus G, that we can write as force by area divided by, I will explain what this delta X and H are. So suppose first we have a material like this, then you apply some shear stress. So the material will be something like this. Okay, so this is our delta x and this is our h. So force by area divided by delta x by h, that is our shear modulus. Now what is bulk modulus? That is change in force by area by volumetric strain. Okay, so this is, we can write a change in pressure by del V by V. So change in pressure by volumetric strain, that is the definition of bulk modulus. Is it clear?
Sir, sir, can you go to the back?
Sure.
Okay, thank you, sir. You can.
You got it?
Yes, sir, I got it.
Okay. So we have something called generalized Hooke's law. So suppose we have a material like this and we apply stress. So this is our x direction. We apply stress in this direction. So what will happen? Material will elongate. Suppose this is our x direction. Okay, so material will elongate in x direction and contraction will occur in transverse direction. In this direction, contraction will be there, and in this direction there will be expansion. So the longitudinal stress longitudinal strain, that is in this direction along x-axis. So this will be, as we know, stress by Young's modulus. This is one part of strain. Other two parts are there also. When you apply stress in one direction, there is also strain generated in this direction, x, y and z direction. This is our x direction we have considered. So in this direction we apply stress, and because of that strain is generated in x direction and also in y and z direction there is contraction. So we can write the transverse strains in yz axis as so this is our Poisson's ratio. That is basically the ratio of lateral strain to longitudinal strain. So these are the true strains that are developed because of this sigma x that we apply in x direction only. Okay, clear or something you have doubt? Is it clear?
Yes, sir.
If someone has any doubt, then ask me. I can explain again. So there is one gate question relating to these relations. I have taken one, there are many questions. So we have to calculate the volume strain using this relation only. But we have to apply the superposition principle to apply. If we applying in three directions, stress in three directions, then we have to apply the principle of superposition. I will explain that. So as we saw, sigma x causes sigma x by E in x direction. Similarly, sigma y, that will cause minus nu, or this we can write also as minus nu sigma y by strain epsilon y by E. Sorry. This we can write because strain is basically stress by Young's modulus. So this in x direction. Similarly, sigma z, that will also produce in x direction. So as we can see, when we are applying stress in 3 dimensions in x, y and z axis, then in x direction only we have 3 components of stress, this one, and this one. So now we will apply the principle of superposition. So our total strain in x direction will be, so we'll take this 1 by E outside, sigma x minus so this will be a total strain in x direction. Is it clear? So we can also
Yes.
calculate epsilon y. So this is the total strain in y direction. This is the total strain in z direction. Okay. So now what is volumetric strain? So that is basically for very small strains in the elastic limit. The volumetric strain we can write as so we have to calculate all the strains in the 3 directions, then we add them. That is the volumetric strain. So what will happen in case of plane stress? So in plane stress we have stress only in 2 directions, that is sigma 1 and sigma 2, and we have to put sigma 3 equal to 0. So where this is applicable, suppose we have a thin sheet loaded in the plane of the sheet. There we have a plane stress condition, or a thin wall tube loaded by internal pressure where there is no stress normal to the free surface. So there also this plane stress condition is applicable. So if we put this sigma 0, sigma 3 equal to 0 in this xyz, also we can write this as epsilon 1, epsilon 2, epsilon 3, sigma 1, sigma 2, sigma 3. So I will put this sigma z or sigma 3 is equal to 0. So I have just put 1, 2, 3 in place of x, y, z, and you just have to put this sigma z, that you have to put 0 everywhere, and you will get the relation. This relation. This is the relation for plane stress condition. Okay, so you all got this, or I have to explain again how these relations are derived?
Sir, can you explain the plane stress condition again?
Okay, so in plane stress, we have stress only in two directions, sigma y and sigma x, sigma y, or sigma y, sigma, any two directions we have stress, and in third direction the stress is 0. Okay, so in this we have to put just sigma, we're assuming sigma z or sigma 3 equal to 0, so we put sigma z equal to 0 in here, here, here also. Then we get these relations. Just put sigma z equal to 0. So this is what I have assumed. You can use it interchangeably. Just put this component 0 in these equations, and you will get these three.
Yes, sir, I got it.
Okay.
Sir, uh,
Hmm.
these are only normally strain, na? Sigma, epsilon 1, epsilon 2.
Yes, it can be normal. Normal strain, actually, we have to go to principal stress. Principal strain, I haven't described that yet. But here you can assume that x, y, z, 1, 2, 3. Thus, generally, I'm considering. I am not going into principal stress, principal strain, all those things right now. But if you assume principal stresses sigma 1, sigma 2, sigma 3, that is also fine. Okay. So you can assume this sigma 1, sigma 2, sigma 3 as principal stresses also, because we are considering only with normal stresses here. So either you choose sigma x or sigma 1, there is no difference. When shear stresses are there, then we have to choose carefully sigma 1 or sigma x. That will be a whole different thing. Okay. Now let's consider plane strain condition. So here, as before, we put sigma z equal to 0 or sigma 3 equal to 0. Here you have to put epsilon 3 equal to 0 in the same equation. Okay, just put this equal to 0 here only. Sigma z everywhere. Put sigma z equal to 0. Basically, these two will be the same. Epsilon x, epsilon y. Only this you have to put 0, so this relation will change. So the relation is this is the same as I have written before here. Just I have put 1, 2, 3 in place of x, y, z. So here we'll put this as 0. So This is a very important condition for plane strain condition. Two stresses are given. If that gives to calculate the third stress, that is the Poisson's ratio times sigma 1 plus sigma 2. It's a very important relation. Okay, so is it clear till now? All those who are joining late, I don't think they will be able to get these things.
Got it, sir.
Got it? Okay, so now we'll go to one question. It was in the first slide. Yes. So a rod is elastically deformed. This is a question from 2016. A rod is elastically deformed by uniaxial stress resulting in a strain of 0.02. Poisson's ratio is given 0.3. What is the volumetric strain? So how to calculate this? So as we have seen, volumetric strain, so we have to simply put this strain already given, that is the epsilon x, that is in x direction. Okay, so that is 0.02 plus, we know when we apply stress in x direction only, there are two stresses that are developed in y and z direction also because of the contraction. So that is minus, so in the y and z direction the strain will be same, because we are considering basically, suppose a rod, that is our x direction, this is y, this is z. Okay, so in x direction strain is given 0.02, and in y direction and z direction the strain will be same, the transverse strain. So that will be Poisson's ratio times strain in the x direction. So this is our strain in the y direction, this is strain in the z direction. Okay, just put the values 0.2, 0.02 minus 0.3 times 0.02 minus 0.3 times 0.02. So calculate this and tell me the answer.
So 0.008.
0.008. Okay, so that is our answer. So is it clear? You just have to put in place of epsilon y and epsilon z this relation. So I hope this is clear. So I'm going to the next question, that is related to the fracture strength, or we can say the Griffith criteria of fracture, brittle fracture. So I will explain this concept. What does Griffith's law actually mean? So Griffith's law says that the rate of change of surface energy should be equal to the rate of change of strain energy. Then only a crack will propagate. So basically when we have a crack in a material, so this is our crack. So for the crack to propagate, two surfaces, on this side one, on the lower side one, two surfaces have to be created. So that requires surface energy. So the surface energy that is required to create two surfaces must come from the rate of change of strain energy. So when this condition is satisfied, the crack propagates. So suppose we take, I'll draw a clean figure. This B is thickness. This is the full crack length 2A. So suppose gamma is the surface energy per unit area of one surface. So what will be the surface energy required, total surface energy? So this is one length is 2A, other is 2A. So 2 times 2A into our thickness B to gamma S. Is it fine? So this is 2A means this 2A and our thickness, that is B, that is going in this direction. So basically we are calculating the area. This upper area, that is 2A times B, also lower one area. So that is why this 4AB gamma S, that is your total surface energy. The strain energy, that one we don't have to derive this, just keep it in mind. So this is not required really. I'm just showing how to derive the main Griffith's equation, that is the fracture strength, how that is related to crack length and surface energy. So suppose in this axis we take energy and here crack length. So the surface energy will straight increase like this, that is US, and the strain energy will go something like this. So the resultant will be something like this. So this is our critical crack length. Okay, so this is our total energy. So when this crack length is reached, there will be catastrophic failure. So for a brittle material, the condition is rate of change of strain energy with crack length must be equal to rate of change of surface energy with respect to crack length. So this is the very fundamental idea of Griffith's law. So actually in principle we should write del 2a because the whole crack length is 2a. We are calculating on the basis of the 2 times a. So just differentiate these two. Here we can remove this b because we are considering unit thickness. Now just differentiate this and you will get the fracture strength, that is 2e gamma s by pi a. So this is our final expression. Is it clear till now? Or anything you want to clarify?
Hello, sir.
Hmm.
Sir, is there any different concept means critical crack length and critical strength means sigma c?
Hmm.
Sir, means how we can differentiate both these two concept means what happens to the materials when it is c critical and second case when it is sigma c.
Sigma c, you are talking about fracture toughness, right?
Fracture
So
toughness is yes,
that
sir. Means yeah.
that is the critical value. So when that value is reached, so after that catastrophic failure will occur. So that is basically the critical value of the stress intensity factor, we can say. So fracture toughness is basically, if you consider for mode 1, this is our expression.
Here A is critical or any length of crack.
No, that depends. There is a trade-off between sigma and A. If your sigma is high, then critical length of crack will be small. If critical length this is large, then this will be small. So it depends how much stress you are applying. If there is a small crack, then you have to apply a higher stress. Okay. So this relation basically tells critical crack for a particular applied stress. So that is this A here. Here also I can derive from here to here we can go. See, so 2 E, that is Young's modulus, that is a constant. Gamma S also, that is a constant surface energy. So if we take this constant, then this will be sigma times pi a. So just take this pi a to this side, square root of pi a, then we get some constant, and this constant is the fracture toughness value here, that is K. See, directly you can go from here to there. This constant is equal to sigma pi a, square root of pi a. Can you see it?
Yes, sir.
So now we'll use this relation here. I hope you already know this type of questions. So can you find the answer and tell me? Surface energy is given, Young's modulus is given.
I think 97.75 like that it's coming.
97.75. Okay, you just have to calculate this. You have to put the values and calculate. That's all. So moving to next question. So what is the concept of CRSS? Critical resolved shear stress. What is this and how to calculate this?
The tau CRS equals to sigma cos phi cos lambda. And phi is the angle between load direction and normal of the plane.
Yes.
Sir, can we show in previous question once again?
Previous question, okay.
So what is the answer
Okay, sir,
of this
thank you.
question?
This one.
Yes, sir. Second question answer.
Second question answered. What was second question? This one. This one someone told, right? 97 point something MPa. You just have to put the values. 2 E is there, 60 GPa, gamma
Sir,
S is
here
given.
A we have, sir, here A we should consider as 1 or 2.
Surface crack length. Yes, you have to consider half of the crack length. If
Then 1, no, sir.
it is
According
given.
to the question,
No, you have to see.
But sir, it is a surface crack, na?
Surface
It
crack,
also
yes.
will.
Surface crack means A is given already. So you have to put just A. If it is through thickness crack or in the middle, it is crack like this I have shown here. So then you have to half it. You could have used 1, but it is surface crack already. So the crack is something like this. So this is A. You don't have to change anything. Okay.
yes, sir.
So suppose this is a FCC material. So what is the plane in FCC? The slip plane, 111 plane, and the direction is 110. Okay. So it is already given. We don't have to consider. So this is our slip plane. This is the direction of the slip direction that is lying in the slip plane. This is the normal to the slip plane. one angle we have, and this is the direction in which we are loading. So here it is given that tensile stress along 110 direction. So this is a 110 direction to activate some of the slip systems. Which one of the following slip system will be activated? So what you have to do
Sir,
is,
B.
yes,
Is answer B.
B. Yeah, you have to calculate first. You have to calculate the schematic factor
Yes, sir.
for
So for
all
B,
this.
it's not coming 0.
It should not be 0. It should be the highest value. So here this cos theta cos phi, this is our schematic factor. The higher this value, the lower will be the stress required. This is our stress. So this is a constant. So if we have higher of the schematic factor, we will require much lower stress to activate slip system. So you have to calculate the schematic factor for all these four systems. Then you have to see which is the highest schematic factor. So that will be activated first. Okay, suppose for one, the direction is, so 111 plane means this is our 111 plane. So the direction normal to this 111 plane will be also 111 direction, and this direction will be 1 bar 10, the first one. Okay. So now you have to calculate cos theta and cos phi. So we know that if we know the HKL values of the two directions, then we can calculate the plane. H1 H2 plus K1 K2 plus L1 L2 H2 square plus K2 square plus L2 square. So this you have to apply for each of these systems, for this and this ones, and for this ones. So then you multiply them and find the schematic factor, and you see which is the highest schematic factor, the easier the slip to activate. So what is the answer?
So B option B, it has 0.25 plus 0.25 limit factor.
Okay, so what are the other values?
So in option A, it minus 0.25, and
Okay,
option C in option D will be 0.
okay, then this is the answer. B is our answer. This is one easy question. So it is given that a perfectly elastic plastic material, that means the graph of the stress strain curve will be like this: perfectly elastic and perfectly plastic.
Sir,
Hmm.
sir, in previous question, to activate any pulley system, why symmetry factor should be higher?
Okay, you see, this is our critical resolved shear stress. This is our stress F by A. Okay, multiplied by the schematic factor. This is our schematic factor, cos theta cos phi. So this is a constant. Okay, so if this is higher, the schematic factor is higher, then this has to be lower. The higher this value, the lower will be this value, because this is a constant. Okay, so at high value of Schmidt factor, we will require small amount of stress to activate the slip system.
Yes, sir.
Okay, so that's why we look at the highest Schmidt factor.
Yes,
So that will be the easiest plane to activate slip.
yes, sir.
Okay, so now here we have to calculate. So it is given a perfectly elastic plastic material, yield stress of 450 MPa.
Sir, is this answer 101.25?
What is the answer?
101.25.
This 101.25. अरे रुक जाओ भाई, क्लास चल रहा है. Sorry, someone was knocking my door again and again. I had to tell him. Okay, so I don't remember the answer here, but I will tell the concept how to calculate this. So resilience is basically the capacity to come back to its original state after it is elastically deformed. So for this region only, where the Hooke's law is applied, the elastic region, the area, this is our resilience. And this whole area is toughness. So basically toughness is how much energy a material absorbs before it fails. Okay, so we have to calculate this, the ratio of this uh, resilience to toughness. Okay, so what are the values given here? Yield strength is given 450 MPa. Fracture at a strain of 0.45. So this is our 0.45 strain. Okay, so we know the Young's modulus, we know the yield strength. So we can calculate this strain. Okay, so this will be our strain. So how much is this?
0.1.
Yes, this is our 0.1. So now I have to calculate the area. We know this value 450, you know this is 0.1. So half So you just calculate and tell me this is the resilience. And for toughness, we have to add this also, this whole thing, plus 0.45 minus 0.1 into 450. So just calculate this and this will be our ratio. You have to multiply 10 to the power 6 also because it is given in MPa. I forgot this. For 15, 10 to the power 6. That's it.
Zero point 0.125.
Yes. 0.125, that is your answer. So one thing you should remember in this tau CRSS that I told. So always we calculate tau RSS, resolved shear stress, sigma applied cos theta cos phi. So when it becomes critical, that means tau CRSS, then we have to use yield strength here. When this applied stress reaches yield strength, then our resolved stress becomes critical resolved shear stress. So this is a constant value. So this depends on the orientation. So when we are changing orientation, this tau CRSS doesn't change, it remains constant. This yield stress, this is our yield stress, so this changes if we change orientation of loading. Then this yield strength in different orientation that changes, but this tau CRSS, this remains constant always. Yield strength
The
changes with
second one,
orientation.
second equation you are telling for perfectly elastic plastic.
Which one? This CRSS?
Yes, sir.
No. Usually when we apply a stress, then we calculate the resolved shear stress for any plane. Suppose you are applying a stress here. So we are calculating, suppose the slip plane is like this. Okay. So we are calculating the resolved shear stress on this plane. So when this stress reaches yield strength, so then we can say that as CRSS, critical resolved shear stress, and slip starts at that point. So we are loading in this direction, suppose. Now if we load in this direction, orientation will be different. Suppose, or we load in this direction, something different than this. In this direction, suppose we load. Then,
Yes, sir. Yes, got
then,
it.
then according to the orientation, the schematic factor will be different. But the multiplication of this, so this is constant always. So if we change the orientation, this sigma ys yield strength will change depending upon the orientation, but this is always constant. So remember this. So this is a material property. This doesn't change.
So what was the answer of previous question?
Previous question, this one.
No, sir. Ratio of length to
Okay.
toughness.
Where did I write that? Here.
Yes, sir, this one.
Hello. So
Yes, yes, sir, yes, sir.
so which one you want me to explain? Like,
No, sir, got it, got it. I got it, sir.
got it.
Yes, sir.
Okay. So anyone has any doubt from the starting to end from this session? This elasticity, Hooke's law, generalized Hooke's law. You can expect always 1-2 questions from this section. The volumetric strain, Poisson's ratio, those concepts should be clear. And also there are some important relations you should remember. Like what is the relation between Young's modulus and Burke's modulus? I'll write it here. So these two you must remember. This is Young's modulus, Burke's modulus. This is Poisson's ratio. This is shear modulus. Now what is the maximum value of this Poisson's ratio? Anyone know?
It's 1.5, 0.5.
0.5 years. Why? Do you know?
Sir, means 0.5 is for plastic materials. So means at 0.5 the closed packs atoms can be only possible. After
Okay, so actually there is one relation as I wrote here, B equal to, you can actually prove it. So I will show it here. 1 minus 2 nu. Okay, so here bulk modulus must be positive always, because they are calculating change in pressure by volumetric strain. So this must be positive always. So Young's modulus is already positive. This is positive. So 1 minus 2 nu. This must be positive to make this positive. Okay, so this must be greater than 0. So this means 1 greater than 2 nu. So Poisson's ratio always must be less than 0.5.
yes, sir. But sir, another proof I think it can be possible if you put the atoms in a closed packed manner. Then also we can prove that for that Poisson ratio is only 0.5 only closed packed atoms.
Because we're considering positive because it becomes negative. If Burke modulus becomes negative, that means when you're applying pressure, the volume is increasing. So that is not possible. Okay, so that's that way you can think. When you're applying pressure to something, then the volume must decrease. So that is the condition we have put here. That's why this is greater than 0. Otherwise, if B is negative, that means with application of pressure, volume increases. So that is not possible. Other way what you are saying you can also prove. There are many ways. Is anyone else has anything to say regarding any question? Okay, so we'll end this session today now. So see you all next week, same time.